Okay, this is the Math 1113 Zoom meeting for March 30th. This will be the only Zoom meeting for this week because Thursday and Friday this week we're on spring break. And we'll hold more. We'll have to double up 7-1 and 7-2 next week. Maybe hold an extra Zoom meeting. We'll see if we can, or maybe I get them both covered in 2 Zoom meetings. I don't know. But yes, we'll do just 7-1, give you an intro to 7-1. This week. Today is the only Zoom meeting for the week. Thursday, 4-1, Friday, 4-2, spring break. We said quiz and WebAssign for 7.1 due Friday. 9. So we won't have them do Sunday like this coming Sunday, like we said. We'll give you an extra week. That way, hopefully you won't, if we make it do Sunday, then maybe you feel obligated to work on them over your spring break. And then, it's not really a spring break, is it? Don't thank me all at once. Okay, 7-1. Trig identities. Trigonometric, maybe a full word, trigonometric identities. Okay, this is kind of a subject unique to trigonometry. We don't waste a lot of time proving or verifying algebra identities or even calculus identities. But trig identities, yeah, we just spend a good deal of time. So they're going to repeat. They showed you these identities. Page 574 is a repeat of identities in chapter 5 and 6. I'll just put them up here. I won't copy them down. I'm going to assume you know them. That a tangent is sine over cosine, a cotangent is cosine over sine, that you get the reciprocal ones, cosecant 1 over sine, etc. And the Pythagorean identities, sine squared plus a cosine squared is 1, tangent squared plus 1 is a secant squared, 1 plus a cotangent squared is a cosecant squared. We showed you these even odd identities in chapter 6. The only new ones are these cofunction identities. And they will have you later in the chapter, have you prove these. It's not hard to do. Right now, just take one and just plug in a number. Let's sine, say, of pi over 2 minus an x equals a cosine of x. And I'll just use x equal, I don't know, 3, doesn't matter. It's an identity, it works for every x. So this is sine pi over 2 minus 3 is cosine of 3. Now you can do this in radian mode, you can do this in degree mode. Just make sure, you use the same mode on both sides. So if I take a sine, turn it on, sine, pi over 2, minus 3. I hit enter and I get this decimal, negative 0.9099. 98999. So if I punch cosine of 3 on the other side, you get the same thing. All right, and then they go for a whole bunch of them. And they're useful for different things, but I can't really show you how or why at the moment. All right, first task. I'm going to have you simplify identities. Maybe I'll try example 1. Page 575. Simplify. Cosine of a t, add a tangent of t, sine of t. Okay. Basic trig facts: sine, cosine cannot be broken down. Every other one can be written in terms of sines and cosines. Other function can be written in terms of sines and cosines. So I can't mess with a cosine, can't mess with a sine. The process of this is to plug in stuff you already know and then see if you can simplify it out. A tangent, hopefully everybody knows, I can put it back up off the sheet, is a sine over cosine. So all I know to do is to sub in for tangent a sine over cosine times sine. All right, well then if I have a sine times sine, that can be written as a sine squared over a cosine. When you see fractions, these are kind of rules for manipulating these formulas, and they're going to come up in verifying identities. Think common denominator. It's tough to explain exactly what I'm doing or why I'm doing it, but I see two fractions that are separate, so I'm going to think common denominator. Put that over 1. The common denominator would be this cosine t, so you times cosine t, and whatever I do to a bottom, I have to do to a top. Well, that'll give me a cosine squared t over cosine t plus sine squared t over a cosine of t. And now with the same denominator, I can crush them together and write it as a single cosine t. And on top, I have cosine squared t, add sine. And I hope the reverse order doesn't bother you, but a sine squared plus a cosine squared is always 1. So this is 1 over a cosine of t. Now that's perfectly legal, and I'd give you full credit. Sometimes the book and everything wants you to write this as a secant t, but it's not like I'd mark this right and this wrong or anything. Sometimes where you end can get a little arbitrary. The book does end, yeah, with these last two things. 1 over cosine t to be a secant t. Basically, this means if I took any value of t and plugged it up here, and I could punch it out, and then I punch in 1 divided by, I can't punch secant directly. If I punch 1 divided by cosine of that same number, I'll get the same decimal. Meaning this formula initially is equal to this. So they're trying to teach some basic algebra skills manipulating these things to prepare you for identifying or to verify identities. Let's try a couple out of the homework here. First two sections of the homework are about simplifying trigs. 3 to 12 here at the bottom are the easier ones. Then they give you some tougher ones from 13 to 27, some nastier ones. They're all building up to start at 29 or 31 here, proving identities. Basically, they're giving you both of these in the first section on both sides. You're supposed to show they're the same. But before I charge into that, let's just try a few easy ones, like number 3 here. So this is page 578. Number 3, and you want to simplify. And they tell you to write your trig expression in terms of sines and cosines. They tell you flat out. See that? Write your trig expression in terms of sines and cosines. And then see if you can simplify it. So 3 is a cosine of t times a tangent t. Well, same trick as last example. This is a cosine of t times a sine t over a cosine of t. Your cosines will cancel. You'll be left with sine of t. So this original expression, take a cosine times a tangent, and it's equivalent to being a sine. Why don't we try one like number 7, a little more complicated. Simplify. The tangent squared x minus the secant squared x. All right. Well, if you look back at your identity, t, 1 plus a tangent, this is what I have memorized, 1 plus a tangent squared of anything equals a secant squared. So you got to be able to kind of relate to an identity and then be able to manipulate it into a form you want. Now this form is tangent squared minus secant squared. Well, if you see this, 1 plus tangent squared minus secant squared, you'll get 0. Because if you subtract your secant squared over, this will go to 0. Move that over, and you'll get tangent squared minus secant squared is equal to -1. Now, I did say to convert the sines and cosines in the direction. Maybe I should have done. I could do it that way too. I could convert the sines and cosines, but I just instantly went to the most direct identity that works, and you should get -1. Give you some confidence in this. I'll use on the calculator. Maybe I'll use x equals 2. So if I compute a tangent squared of 2 minus a secant squared of 2, I should get -1. Now you can't punch secant squared directly. Let me come down here. You would punch tangent 2, and then you put it in parentheses to square it. You can't punch it like this. Minus 1 divided by cosine of 2, and you put that in parentheses squared, and you better get -1. And I mean, you can use any number at all. You can use any, these are identities, they work for every number. Okay, so now I could punch tangent 2 and then square it separately too. So I could punch tangent 2 and square it. Or maybe I should just do it all at once. All right, so parentheses, tangent 2 squared minus parentheses 1 divided by cosine 2 squared. Anybody want to give me a drum roll? Like a little drama. There's a ton of parentheses on this. Enter -1. Always, and it doesn't matter about the 2. I mean, there's nothing magical about the 2. No matter what number you use, you're going to get -1. All right, why don't we try a couple out of the next section? Why don't we try 13? Sine x, a secant x over a tangent x. Simplify. Well, again, you can't mess with sine, but a secant is 1 divided by cosine. Tangent is a sine divided by a cosine. You should be able to probably tell sine divided by cosine, but you're going to get 1. But I'll go ahead and finish it up. Over cosine over sine x over cosine. Your sine x times 1 up there stays over the cosine. So you're getting sine x over cosine x times cosine x over sine x. Remember, you got to flip this and multiply, and you can see everything canceled, giving you 1. So I can plug any x into this, punch it correctly, I will always come up 1. All right, what's something that looks a little more, well, look at one like 17. This will bring in some factoring. Take a cosine cubed, add a sine squared cosine. Okay, well, we see something like this. There's no identities for a cosine cubed. So the idea is to look at this. Direction, say, simplify it. You should notice a common factor of cosine. Take that out, put a big parentheses, and now you're playing the game. Well, cosine times what is cosine cubed? Hopefully you know that's a cosine squared. So cosine, see there's a 1 there, powers add and give you that. And your cosine coming out leaves you your sine squared. Well, I hope you recognize, of course, this comes up everywhere, in every combination. Add a sine squared to a cosine squared, you always get 1. They can be separated by pieces, 3 or 4 pieces. If you get a cosine squared over here and a sine squared, way on the right, you can knock them out and call them 1. And so then a cosine times 1 is a cosine. So this entire nasty thing is just simply a cosine. All right. Why don't we try one like 27, just to set up again some of these identities. Simplify. 1 divided by a sine. 1 minus sine alpha, that's called an alpha, plus a 1 over 1 plus sine alpha. I don't know if this is enough to make somebody go, ah! But again, C fractions, think, common denominator. Now, that pretty much means you're going to have to be able to put these together, meaning you need both of them. 1 plus sine alpha. Both pieces, they're different pieces. You got to both be in your common denominator. And then you got to think, what did I do to up here to get to this? Well, in effect, I moved this over. So if I did this to the bottom over here, then I'd do it to the top, and that would give me a 1 plus sine alpha up there. Well, then I move this one over here under here, so I've got to do it to the top, plus 1 minus sine alpha. You're really multiplying by these ones, but that doesn't change. If there's anything other than 1, you'd have to multiply through by something. But well, looking and simplifying the top, and you can see your sine alphas cancel, and you're left with a 2. Plus plus 1 is 2. Your sine alpha minus sine alpha, gone. Well, maybe it's fully simplified, maybe not, but let's FOIL on this bottom and see if we get anything. All right, hope y'all remember your foiling. 1 times 1 is 1. 1 times sine alpha minus sine alpha times 1 minus sine alpha times sine alpha is minus sine alpha squared. All right, we'll take a look at your like terms, and your sine alphas cancel. 2 over 1 minus sine squared alpha. Now, I don't know if you've seen that form of it, but just to point out, sine squared plus cosine squared equals 1. So you can get one or the other of these. I want a 1 minus sine squared. If I move 1 minus sine squared, I'll get a cosine squared. 1 minus a cosine squared will be a sine squared. 1 minus a sine squared will be a cosine squared. So this is 2 over a cosine squared. Now I consider that fully simplified. Some, the book may or may not like the fractions, so you can write that as twice secant squared. When you flash it up, it becomes a secant squared. All right. Okay, let's talk about trig identities. Yeah, I teach it, I can't even spell it. Trig identities. Oh, sorry about that. Maybe I prove I can. All right. Basically, they take two expressions and expressions, set them equal. And the point is they are equal for all, quote, x, but you don't always use letter x. Sometimes you use t, other letters, for all the letters. Okay, I'll just plus cosine squared is equal for all x. Okay, now we will never verify this. We will use basic ones like this, and sub them in to the ones in the homework. To prove or verify them. I'll start with 31 if I went too fast. To prove or verify them. Okay. Page 579. Try one like 31. Notice the directions. they kind of give you, they kind of use both words, prove or verify. So the kind of the title is proving identities, and then you verify the identity. 31 says that a sine theta divided by a tangent theta equals a cosine. I'm going to start off with one that's pretty simple. The idea is to verify this. Okay, well, you're going to do the same thing we did in those first two sections, except in those first two sections, they like give you one little side of this, and then you'd sub stuff in and simplify it down. All right, but the game here, this works for every theta. So you can play this game really one of three different ways. Three different ways. Okay, one, you can start on the left side. We'll call this the left side, and this the right side. You can start on the left side. The left side, and turn into the right side. You can start on the right side and turn into the left side, or you can start on the left side, get so far. If you can't figure out what to do, work on the right side, or vice versa, and meet in the middle. And a lot of them will work any of these ways. So if I do number one on one and you do number two, as long as it works and verified and every step's legal, then it's fine. You don't have to do them exactly the same way I do them. All right, back to 31. Verify sine theta divided by a tangent theta equals a cosine theta. All right. I'll just point out some of the book steps. The book kind of writes these, and I won't copy these down. I've written down some of these, but here's the guidelines here. Start with one side, pick one side and write it down. Goal is to transform it to the other side. It's usually to start with the more complicated side. So you can start on the left, work to the right, or start on the right, work to the left. Use known identities. Bring fractional expressions to a common denominator. Use fundamental identities to simplify stuff. And number three, if you are stuck, you can always convert to sines and cosines. See if you can get it in terms of sines and cosines. And that's basically what's going to happen here. A tangent is a sine over cosine. What you got to do is treat it like there's a wall here. You don't multiply through by the same stuff. That's treating it like an equation. It's not an equation. This is not an equation. Equations you solve for one number or two numbers or that work. This works for everything. Don't multiply through. By a number. That's treating it like an equation. Okay. So you want to treat it like it's a wall. this would work out as sine theta times a cosine theta over a cosine sine theta. This flips. Sine theta cancels. And you're left with cosine theta. And on the other side, you have cosine theta. And that's how you know the game is done. It's when one side turns into the other side. All right, we'll try a few more here. Why don't we try one like 35? Well, 33, I guess. Page 579. A cosine of u, secant of u, over a tangent of u is supposed to be identical to a cotangent of u. See, we'll start here. This looks more complicated than this. The only thing you really do to this is write it as a cosine over sine, and that doesn't look like this. So we'll go with cosine of u. Secant is 1 over a cosine of u. A tangent is sine u over cosine u. And again, we're treating it like there's a wall here. Well, up here, the cosines cancel. This gives you 1 divided by sine u over cosine u. And that will give you 1 times cosine u over sine u. You could stop right here. That is the definition of a cotangent u. But if you want to, sub in cotangent u then equals cotangent u, that's fine too. You have verified this identity. All right, why don't we try one like 35? It looks a little nastier. Page 579. A tangent over a cosecant of y is 1 over a cosine of y minus 1 over a secant y. I always wondered when I was a student learning, where did they come up with these things? Who thought this up? Well, you could write this as a 1 over sine, play around with this, but I hope it's obvious you're never going to turn that into these separate fractions. So when I see separate fractions, I instantly think, let's play common denominator and see what we get, and maybe we can turn it into this, or this might be a candidate to turn, kind of meet in the middle. Who knows? It's hard to look into your crystal ball. Well, when I come over here, I would really, let's see, I could leave this alone, but then you got, secant y up there, cosine y. Try to look into my crystal ball. I think I'd rather turn this into a cosine first. All right, so that's 1 over a cosine y. Again, there's a line here. And minus 1 over a cosine y. All right, well, that's going to flip around to be a cosine y. That's a minus, my fault. Minus a cosine y over 1. See, you're going to get 1 times cosine y over 1. Right, well, now you can make your cosine y your common denominator. Common denominator equals your cosine of y, which means you're putting it over here. Write it out, 1 over cosine y minus cosine y over cosine y, which means I got to put 1 up here. These would cancel and you're left back with this. All right, well, that's going to give you 1 minus cosine squared y all over cosine y. Probably going to need second page on this one. Notice it doesn't seem to be getting anywhere close to this. But if you remember a 1 minus cosine squared y, that's equal to a sine squared y. Cosine y. Now, at this point, I could work on this side, trying to turn this into, see, now I got my single fraction. I could sub in sines and cosines here and see if I could turn it to this. Or, if I'm really stubborn, see, I could spread this out. A sine squared can be busted back as a sine y over, and you can put the cosine y under either one. Now, if you'll notice, this is your tangent y. That equals your tangent y sine y. All right, well, now I've got my tangent y matching, but it's times sine. Up here, it's divided by cosecant. Now, I could either write this and put the cosecant up and make it tangent y sine y here, and boom, I'm done. Or I can put this sine y down, and then it becomes tangent y divided by cosecant y. If you change levels with these things, they go to their reciprocal. And over here, I've got tangent y divided by cosecant y, and I'm done. So yeah, there can be multiple ways to do these things, which is what makes it kind of hard to teach, and I guess probably kind of hard to learn, because there is no real single correct way to do these things. Why don't we try something like 45? Brings in a little more algebra steps. 45, page 579. We get time for maybe 2 or 3 more. Get y'all started. A tangent of x plus a cotangent of x, and that's squared, comes up as secant squared plus a cosecant squared. Again, who thought of this? I have no idea. Okay, this is kind of, again, which side do I want? I'm looking at my crystal ball. Which side of do I want to work on? I think I'd rather bust this out of your square. Are y'all good foilers? Maybe I should write it twice. Cotangent x, tangent x plus cotangent x. Remember, FOIL, this times this, this times this, and this times this, this times this. All right, so I got a tan squared plus a tangent, cotangent. I'm going to need more room if I'm just going to stay on this half of the paper here. Then plus a cotangent, tangent, plus a cotangent squared. All right, now take a look at this tangent, cotangent, or cotangent, tangent. Remember, these are inverses. When you multiply something by its inverse, you always get 1. If you want to see it, put a little fraction, put this down, and you get a tangent. Tangent to cancel, same thing here. Put this down, you get a tangent. So here's a 1 plus another 1. Really, you get 2. Tan squared x plus 2 plus cotangent squared x. Okay, but it doesn't look like this. Oh, this is where, like I say, I don't do these in advance. You have to think them up on the fly here. Whew. Are we ready for sines and cosines? What do I want to do here? Always go to sines and cosines. I could stick to tangents. That would be easier. Which gibberish do I want to do here? Why don't I just stick to tangents for the moment? Tan squared plus 1 over tan squared. Oh, no, maybe that's not. Sometimes you do something and then I don't know, because if I get common denominators, I want to tangent fourth. I really don't want to do that. I could go to sines and cosines. Maybe I should. Yeah. Okay, so here's a sine squared over cosine squared plus a 2 plus a cosine squared over a sine squared. I'm kind of going back to this line. Common denominator, you get 3. Yeah, this is what I'm saying. You know, I kind of want to give up on this. Let's work on this. See where I go. I hope I'm not wasting y'all's time. I'm sure I can get this. All right. Well, you're going to get a 1 over cosine squared. You get a 1 over cosine squared and a 1 over sine squared. Let's see if I can turn this into something like this. All right. Well, you're going to get your common denominator. I'll write it sine squared, cosine squared. Switch the order, but for some reason it was like sine first, then cosine. All right, now remember that's going to give you a sine squared up here, going up there, and then plus a cosine squared. Okay, well, that top is 1 over a sine squared squared. That's a cosecant squared times a secant squared, which doesn't really look like this. All right. Probably some of y'all have already got it. They're screaming at me. Do this, do this. Let's think common denominator here and see where we can go with it then. So your common denominator here, go cosine squared sine. You need both of these pieces. Now, can you tell you're going to get a sine cubed? You got to kind of think with 3 pieces what would cancel back. So if I put this together, I'm going to need a sine up here, which makes that sine cubed. So you see if the sine cubed cancel the sine, you're left with sine squared over cosine squared. In the middle, you'll have 2 cosine squared sine. You need both of them with the 2, so these would cancel this, leaving you just the 2. Over here, you're going to need a cosine squared. There. Actually, you're going to need cosine fourth, aren't you? You put a cosine, you just need a cosine fourth. Because it's like you're putting the cosine squared here to make this. So you need a cosine squared up there, making cosine fourth. There it is. So then that leaves you, if this canceled this, you left with cosine squared over sine. Yeah. I think I am totally butchering this one. I just don't see where to go. If I pull out a sine, I'd be left, I could factor a sine out of the first 2. I'd be left with a sine squared plus twice cosine squared. That doesn't help. Get that darn 2. Well. Anybody's watching this far. Just looking back through, oh, I spot something. That's a cotangent squared. So that should be cosine squared over sine squared. Aha. No wonder I'm screwing up. My apologies. There should be a sine squared there. So when I do my common denominator, I get cosine squared sine squared. So this has got to be a sine to the fourth. Yeah. That's a sine to the fourth. So this, we cancel this, leaving me sine squared over cosine squared. Okay. This is a sine squared. It's plus 2 sine squared cosine squared. And then you got your cosine fourth here, which leaves cosine squared over sine squared. Bingo. I lost a square right there. My apologies. Okay. Take a look at the bottoms now. Bottoms match. Bring this down 1 over cosine squared sine squared. Bottoms directly match. So I win this game if I can show that this entire top is 1. Because it clearly is. No screw up on that side. So this is a complicated kind of factoring. But I think you'll find you can factor it as sine squared plus cosine squared x, and another sine squared. I'm guessing you don't want me to put a whole bunch of these on the test. I don't know if you can see the factoring or FOIL back. You'd get sine squared, your sine to the fourth. You get a sine squared, cosine squared, plus another sine squared, cosine squared from here. There's your 2 sine squared, cosine squared. Cosine squared is your cosine to the fourth. Individually, notice the sine squared plus cosine squared plus individually, these are 1. So you got 1 times 1 cosine squared x sine squared x equals 1 over cosine squared x sine squared x. Well, I probably did that the most god-awful backwards way, back-asswards way possible, but I did get there. There may have been a lot easier way that completely threw me. But in any case, there's a case of meeting in the middle. If you saw an easier way, feel free to write it down, email it to me, and feel free to call me an idiot. Why don't we try a couple more here? We're at almost an hour. How about one like 51 looks pretty complicated. If I could butcher it. Sine squared x minus cosine squared x. Inside you get, don't worry about all these dots, sine minus cosine squared x, and on bottom a sine x minus cosine x squared. Well, each side looks kind of equally complicated, so I guess here's another FOIL. I don't know if you need to see it written twice. Sine x plus cosine x over sine. There's no way to simplify sine squared minus cosine squared. Actually, there is, but we haven't shown it to you yet. All right, FOIL this out. Sine squared plus sine cosine round one. I like to teach it as round as trinity property. So this times both, that's round one. And this times both, I'll write that second piece as plus sine x cosine x, and then plus cosine squared. And you're all over sine minus cosine squared. All right, well, notice that sine squared plus your cosine squared on the end. Again, they're separated by a bunch of pieces, but it doesn't matter. Doesn't matter the order you add things. I could easily switch that back, write them together if it makes you feel better. But that sine squared plus that cosine squared, that's 1. Plus, and a sine x cosine plus a sine x cosine, that's 2 sine x cosine x. Now, I could do a difference of squares and factor the bottom, but I don't see how it helps you much. Well, actually, it might. Who knows? Let's factor that as sine x minus cosine, or plus cosine, sine x minus cosine. I'm kind of stuck. Don't really see any identities. So sine squared plus a cosine squared would give you something, but not single powers. This looks like a case of meet in the middle to me. So why don't we come over here and factor the top. If I can write sine x plus cosine x, sine x. This is times these. I'm kind of out of room to do this. Maybe I should do this. Maybe I can spread this out. Here's the right side. Got this to right side here. All right, let me come over here and do left side. Maybe I can get it on this way. Left side. Squared minus cosine squared minus cosine x. All right, factor the top plus cosine. Still out of room, times sine x minus cosine divided by, all right, can you FOIL this? Have you done the FOILs now? Sine squared, square the first. Your middle term will be minus twice sine x cosine x. And your end term will be a positive cosine squared. So you will get a sine x plus cosine x, sine x minus cosine x. And your bottom, again, see that sine squared plus your cosine squared, 1 minus 2 sine x cosine x. Okay. Let's FOIL your top. This probably goes a lot better in a big old chalkboard than trying to show it on all these papers. Sine squared minus sine x cosine x plus sine x cosine x. Well, actually, that's a minus cosine squared. Oh yeah, I'm back to this. Idiot, I've gone in circles. Over 1 minus 2 sine x cosine x. Idiot, I've gone back in circles. So I've gotten sine squared minus cosine squared, 1 minus 2 sine x cosine x. This is my left side. All right, so at the moment, this looks like my right side, and this is what I've gotten for my left side. Trying to do something intelligent here to Apparently I'm picking nasty examples here. Let me pause the record and play around with this. I don't waste y'all's time. Okay, sometimes you have to kind of completely give up in frustration and start over and give yourself a completely different approach. I'm going to show you how easy 51 is and then compare back to what I was trying. I'm foiling stuff out. I'm getting nowhere. Been a while since I've done these. Cosine x squared over sine squared minus cosine squared. The other side, you get sine squared minus cosine squared over sine x minus cosine squared minus cosine x and then squared. Okay, expand this out. Don't FOIL. And FOIL. And what I mean by that is just write it sine x plus cosine x, sine x plus cosine x. Okay, so I'm working on the right side. Factor. It's a difference of squares. You'd get sine x plus cosine x, sine x minus cosine x. And then take a look. This cancels this. And you're left with a sine x plus cosine x over sine x minus cosine x. And there's nothing really you can do with this. So this is the right side. It's a lot simpler than what I had over on my first attempt. All right. Play the same game on the left side. Left side. Factor the top. Sine x plus cosine. Sine x minus cosine. On the bottom, just expand it out, but don't FOIL it. Sine x minus cosine. Sine x minus cosine. And then take a look. That entire factor cancels that entire factor. And you're left with sine x plus cosine over sine x minus cosine. And if you'll take a look, if I get it on the same page, there you are, you completely match. Like I said, sometimes, you know, it's a trial and error kind of thing. And FOILing stuff out just leads to massive gibberish and frustration on my first attempt. So if anybody followed this far in, you know I'm an idiot. But I did get it a lot quicker. It's not always necessary to FOIL. Okay, we're way over an hour, so I hope that's enough to get you started, and we will have some more Zoom meetings next week. This is the last Zoom meeting for this week. I know that breaks your hearts. That should be enough to get you started. We'll have more Zoom meetings next week. More Zoom meetings next week. Over 7.1 and 7.2. We'll have to double up a little bit because this is a short week. Hope that's enough to get you started. We'll see you next week.